With our new unit and final unit starting today, we're kicking things off with linear versus non-linear relations, and specifically in the unit quadratic relations. Now, these are things that you are going to see in grade 11, so it's advantageous to just get a general understanding of what linear and non-linear relationships are and those characteristics. So if we talk about the linear relationships that we discussed earlier on, the equation of a line, we have an example here. The exponent on the x value is 1, so there's no exponent. So if I look at the table of values and plug in my x value, when x is 0, what does y equal? Well, I plug those values in, I receive different y values. So if I calculate my first differences, my second y input, subtract my first y input, 4 minus 2 gives me 2. 6 minus 4 gives me 2. 8 minus 6 gives me 2. So we see that the first differences are the same, or that they are constant. If we have an equation with an x squared, or it has an exponent greater than 1, we see something here. I go ahead and plug in the same x values into the equation, but then fill out the math. So when I plug 1 in as x, 1 squared is 1 plus 1, and then I do that throughout the same. And then I take my second y value and subtract my first y value. 2 minus 1 is 1. 5 minus 2 is 3. 10 minus 5 is 5. So the first differences are not constant. So if I was to go ahead and graph these, we know that a linear graph would look like a straight line. If we were to go ahead and graph x is 0, y is 1, x is 1, y is 2, what it would look like would be a bit of a curve here. So I'm just going to zoom out real quick, and we can see the difference here. So all of our linear relations on the left-hand side, all the things that we already know when we talk about first differences, and the nonlinear relations, their first differences are not constant, which means the graph looks a little bit different. So, too far. So quick recall, the equation of a linear relation is in y equals mx plus b, where m is the slope. First differences in a linear relation represent the slope of the line, right? So in our first differences, we have when x is -2 and y is 4, x is -1, y is 2, and we can calculate the first differences, and we end up getting the same or constant first differences, which would be otherwise known as the slope. So the slope of this line is -2, and the graph of that line would look like this. And this is a linear relation, and the slope is -2. That's just kind of finishing out example A. Example B, we have our x values and our y values. If we calculate our first differences, they are not constant. They are not at the same rate. So we know that this line, or the relation, is nonlinear, which means that we don't have a constant slope. There is no constant rise over run, so therefore there is no slope, because this line is curved. So the quadratic relation, a quadratic relation is a type of nonlinear relation in the form ax squared plus bx plus c. Now we saw this last unit when we were factoring trinomials. This is a trinomial. Just so happens to be the quadratic relation. So the highest exponent on the variable is 2. That's how you know it's quadratic. When you see the exponent of 2 on x, you know that it is a quadratic equation. So table of values, I have x values and I have my y values when I plug them into my example question here. My first differences are not the same. I have -3, then -1, then 1, then 3. But if I was to take the second differences, so then this value minus this value, I end up getting constant second differences, right? So the first differences are not constant, therefore it is nonlinear. However, the second differences are constant, right? We can see that here, which means that this is quadratic. So when the second differences are constant, it is quadratic. Another way is like looking at this and like, oh, it has the degree of 2, it's quadratic. The graph of a quadratic relation appears as U-shaped curve, and this is called a parabola. So a parabola is symmetrical. When divided in half, the two sides are mirror images of each other. And you can see that here. It looks like the letter U, and each point is symmetrical to the other. So if I look at just the right side here, and I look at this point here of 2 and 5, well, from the x-axis, it's 2 units over. But when I take the negative 2 and I square it, I end up getting the same on this side. So the parabola is symmetrical because they are mirroring the sides of each other. Bit of a worksheet here. If you take a look at the other video that I uploaded, it does a very good job of showing all these different relationships and what it means to be a quadratic relationship and what the parabola looks like and why those are symmetrical.